gentlemen. My name is Dr. Umish Srivastava. I am Executive Director with Indian Oil Research Center at Faridabad. And I'll request my friend Mr. Mantri to take the session forward.
Sure. Thank you, Dr. Umish. Hi, good afternoon, everyone. My name is Anand Mantri. I'm a senior principal with Kearney. It's a management consulting firm, and we do a lot of our work on the business side on green hydrogen and so on and downstream. Welcome to the session. Without any further ado, I would want to introduce our speakers and their topics, and then would invite each one of the speakers to come forward, present their ideas, and take a tentative time of 10 to 12 minutes and then leave the rest for Q&A. The first speaker for us is Mr. Steve Raju. He's the CEO of Alphios Finergy Private Limited. Just checking if he is here.
Yeah, Mr. Raju is there.
The topic is that he'll focus on is decarbonizing the industry with clean hydrogen, and that too from methane splitting. And I think the last two terms are the most important in terms of the newness of this presentation. Welcome on board, and over to you.
Thank you to all the distinguished guests here. I just want to say that it's such a great privilege that a startup of our status, which is very young, less than a year, to be having this sort of a platform. And I want to thank the moderators as well. So without any further ado, I'll continue. Decarbonization has always been the challenge for us, but with green hydrogen as a pivot for it, we have to accelerate it further in an economy like India, where each and every rupee matters. And globally, the iron and steel industry contributes to almost 9 to 10% of the carbon emissions. But in India, as a single source, it's almost 46%. So why is green hydrogen the pathway for DRI and EAF? So out of the many strategies that's being said, the DRI platform with an electric arc furnace is the key platform for us to decarbonize steel production. And by a study by McKinsey, it has been said that almost 30% of the natural gas that has been injected as a clean source can actually be eliminated and green hydrogen can be produced. And only a minor retrofitting is required. There hasn't be any uphaul, there hasn't be any major changes that's required in the current infrastructure. However, if you can look at the cost of green hydrogen, this is a study done by Niti Aayog in connection with an RMI, and it said that the cost of the electrolyzers, for which 55% is the balance of plant. Now, I just want to point out here saying that out of the BOP, 22% of the cost is the deionized water, so which is the pure water that's required to produce hydrogen. And in an economy like India and in even other major economies, which is water stressed, and there's a lot of water scarcity. We come from the city of Chennai, and just a couple of years ago, we actually faced ground zero water levels. So in order to truly bring down the cost of green hydrogen, we first have to bring down the cost of the stack components, which is 45%, and then the deionized water. Now, you might think the renewable electricity intermittency could be the challenge why green hydrogen is so expensive. But just over a decade ago, green hydrogen was almost, solar was almost $3 to $4, but now it's gone down to 3 or 4 cents a unit. So as economies of scale grow, we are seeing that the cost of green hydrogen will also go down because of its complementaries. So as you can see from the chart here, the renewable energy source for hydrogen, as well as the electrolyzer, comprises to almost 55 to 60% of the cost of green hydrogen alone. So having made radical changes here and not having a structural change will not actually be helpful for India to actually accelerate forward. So one way, what we devise as a strategy is to change the feedstock by making industrial wastewater or any water usable for electrolyzers in India. Because as India is a water scarce country, it is imperative and it is critical at the moment that we don't rely on pure water, but rather we should be able to use any water for it. And the cost of renewable electricity is also coming down. So all of these are advantages for us to accelerate our movement forward. Now, a lot of the high temperature electrolysis with solid oxide or with steam electrolysis has been demonstrated to have very good efficiency, but on a cost economic perspective, low temperature electrolysis is where the key arises. And in an economy like India, where the cost matters, alkaline water electrolysis could be the most powerful and could be the most useful sort of electrolysis method because it has a TRLR of almost 8 to 9, and it is the most advanced of all the electrolysis technology. However, the electrolysis of water itself is an inefficient process where 65% is the efficiency that's required, and the rest is let out in round cycle efficiency. At the same time, it is also, CCUS is also very expensive in India, that it is not a practical solution for us to actually move forward with CCUS, although it might sound good and it looks like a very good dream, but it is actually not practical in an economy like India where CCUS remains expensive. So that is why we believe that co-electrolysis is the way forward, that we have to step away from the vestiges of normal hydrogen production and we have to make it some more innovative, that where innovation can happen not just in the regular method of green hydrogen, but also other electrovaluable fuels and also other electrovaluable resources. And we will say why Alphios, our startup, is pioneering this way. And even in, as long as the cost of green hydrogen doesn't go below, the cost of producing green hydrogen doesn't go below 50 kilowatt an hour, we don't see any practical point of continuing this sort of method unless we bring in a radical change. But co-electrolysis has its challenge because co-electrolysis typically has been done in a way where H2O and carbon dioxide is done in a single vessel. And as a result, there is a phenomenon called as cathode flooding, where the CO2 has a tendency to form carbonates and bicarbonates, and this actually leads to corrosion of the electrode materials. So it is imperative that we develop non-platinum group metal electrodes and as well as electrodes that actually are resistant to these terms. So as you can see, a solid oxide electrolysis, which operates at very high temperatures of 800 to 1000 degrees Celsius, have been quite innovative in leading the industrial scale production of CO2 electrolysis. But again, where cost economics matter and when it comes to raising the economies of scale, I think low temperature electrolysis without the impediments and with actually improving the technology would be the way forward. So this is where we introduce our co-electrolyzer. So our co-electrolyzer is Alphios. And here, the trifecta that we bring here is the industrial wastewater as a feedstock as compared to the deionized water or the pure water. As at the same time, we introduce a stack, a PEM cells-based CO, which actually converts the CO2 into solid carbon. So unlike typical electrolyzers, which gives the output as hydrogen, which is green hydrogen and oxygen, our co-electrolyzer gives the output as solid carbon and green H2 and O2. So we use a modified flow cell technology. Typically, a lot of the electrolyzers in CO2 electrochemical reductions use a H-type cell or they use a modified electron membrane. But here we are using a flow-type cell, which is cheaper in value, and it's made with earth-abundant materials. And at the same time, it actually leverages the thermodynamic equilibrium because, as I've just mentioned earlier, that electrolysis is an endothermic reaction and Sabatier reaction, which is CO2 plus H2O that gives out methane, is an exothermic reaction. So combining these two in a single vessel, but separately as two electrolyzers with a PEM cell, can actually yield a better result, and we can actually leverage the thermodynamic equilibrium from 65 to 90 degrees or even to 100 degrees with the improvement in electrocatalytic materials, with the improvement in cell performance, and with the improvement. So we are developing a bimembrane as well as a bifunctional catalyst at IIT Madras, who is helping us with this technology. And we believe that sooner in the future, in less than a year, that we'll be able to have an industrial scale prototype of our electrolyzer. Now, why is Alphios superior? In this way is that we use industrial wastewater, and industrial wastewater tends to be the most corrosive form of all wastewater. But however, the advantage here is that a lot of the industrial wastewater tends to have microbial activity. So with a simple photochemical reduction or with a simple microbial removal methods, you can actually remove the impurities, and this water can be fed into the electrolyzers. And our core methodology here is that our electrodes can actually withstand all of these corrosions and all of these impurities. And second, our bifunctional catalyst as well as our flow cell are indigenously made, which means that we don't depend on elevated temperatures, we don't depend on thermal waste heat. It's all completely electrochemical, which means that it can be easily be adopted into Indian SMEs and MSMEs, which is the backbone of the Indian economy. Now, if decarbonization has to happen, it has to happen through the SMEs and MSMEs, where green hydrogen acceleration and adoption of green hydrogen is actually proliferating. Now, one more point is that a lot of the times what is actually clearly left out is the valuable electrofuels. That is the C2 and C3 and even C1 chemicals. So with our electrolyzer, not only are you getting green hydrogen and oxygen as your output, but also solid carbon. And solid carbon, depending on the applied potential, as well as the electrocatalytic environment, you can create formic acid, ethylene, even green methane for that matter, which will be a big catalyst for India to be self-reliant on its methane emission. So this is the study, again, done by Niti Aayog and RMI, which shows the market capacity and the market growth of electrolyzers in the future. As you can see, there's almost a 20 times jump from 2022 in almost in 2 decades. So green hydrogen, as Dr. Umish had pointed out, will be quite useful, and it'll be ubiquitous in many environments, and not just in the steel industry. Although I started with the steel industry, depending on the point of emission, but it'll be ubiquitous and omnipresent in many industries and will help in accelerating decarbonization. And so this is a simple statistics and a table that we prepared. If we are to scale our electrolyzer to 1 megawatt or beyond that, what are the cost advantages we'll have once we achieve the economies of scale? And how much can we bring the price of green hydrogen at scale and at economies of scale? So in the market without the subsidy, it's around 640 rupees or $8. But with the cost advantages because that you get from a capex reduction, because you don't use any of the platinum group materials, or nor do you use any of the very expensive electrode assembly materials. We use everything indigenously, which means that you can cut the capex cost by almost 35 to 40%. And with the adoption of renewable energy and with the adoption of renewable items for our installation cost, we can actually subdue a lot of the other intermittent cost that's being involved. So this is our team from IIT Madras. That's me. And my partner Bharathan is also here in the audience with us. And our technology head is Dr. Sundara Ramprabhu, who is the Institute Chair of Physics at IIT Madras. Thank you for the presentation, and thank you to this team.
Thank you. Thank you for this interesting concept. We'll take the Q&A towards the end, but thank you so much to keep it short. Thanks. Next one is Mr. Appala Raju. He is Senior Technical Manager at HPCL, and he will talk about changes in technology selection and setting up green hydrogen facilities in refineries, which obviously will be the first off-takers of green hydrogen, as all of us are aware. Over to you, Mr. Raju.
Good afternoon, one and all. It gives me immense pleasure to speak here. Today my topic is challenge. HPCL is first time installing green hydrogen project in its Visakhapatnam refinery. So what are the challenges we are facing today? I am present that topic. This is the legacy of HPCL. Since 100 years our company is operating, and in 1974 HPCL is established. In 2019 we are getting Maharatna award. At presently we are one of the Maharatna in the Indian organizations. So these are the types of hydrogens. The grey hydrogen, which is generated from SMR technology, steam methane reforming technology. After that, in this process, CO is generated. CO2 is generated. Once those CO2 is captured, then it is called the blue hydrogen. So one pyrolysis method is used. It is the Tarkus hydrogen. The green hydrogen predominantly uses the electrolysis method, which is generated from the water. This is the history why HPCL is converting, setting a green hydrogen plant. HPCL requires hydrogen for their secondary processing units to treat MS and diesel to reduce their sulfur levels. For that, we require hydrogen at 99.9% purity. Further, we have a hydrogen generation units which are generating using SMR technology. In that, we are getting more than 20 ppm of CO2. So, as per Ministry of New and Renewable Energies, so we need to set up 0.158% of carbon emission minimization. Accordingly, our calculations we need to set up a 370 TPA of hydrogen plant. For that, we are moving forward in 2022. So we given the order for set up a green hydrogen plant with 370 ton per annum. The order is given to Technip. Technip is the EPC contractor for us. So this is the project details. Capacity is 370 TPA and the power requirement is 2.6 megawatt. DM water consumption is 0.5 meter cube per hour. And the technology is a bipolar alkaline electrolyzer. The aqueous solution, we can use NaOH or KOH. We are going for KOH solution. Our EPCC is Technip. So these are the two types of technologies available. One is the alkaline electrolyzer, which is a conventional method, and second one is the proton exchange electrolyzers. So in alkaline electrolyzer, we are using diaphragm to separate anion and cathodes and anodes. So whereas in PEM, we are using membranes. So out of these, in alkaline electrolyzer, the hydrogen is separated from the water at a cathode, and its hydraulics atoms are moving towards the anodes through diaphragm. So whereas in PEM, so oxygen is generated in anode first, and followed by reactions are happened at a cathode. So this is the block flow diagram of setup. We are taking DM water, and through DM water pump, it is going to the hydrogen tower. After that, it is moving to caustic water solution pumps, and it is moving to followed by electrolyzer, where the hydrogen and oxygen are separated. These two separated gases are went to their towers. After that, the temperature is around 80 degrees centigrade and the pressure is 30 bar. So after the separation, these both O2 and H2 streams are cooled, and hydrogen is sent to further purification process, and O2 is emitted to the atmosphere. This is the hydrogen purification process. Once hydrogen is generated in electrolyzer, it is going to the deoxy column, where the trapped oxygen is separated. After that, it is cooled to normal atmosphere temperature and going to the mist separator, followed by dryer column to remove any dust particles, and it is going to the hydrogen header. These are the catalyst and chemicals required for us to operate the green hydrogen plant, and the life of each equipment is also provided. The electrolyte, that is the solution, we need to change in every year or 1.5 years, and deoxy catalyst life is 10 years, and zeolite molecular sieve is for hydrogen drying facility, it is a 5 years life. These are the effluents is generated from the plant. Solid effluents nil, gaseous is oxygen, which is vented to atmosphere, and some of the hydrogen traces will be there, and water is rejected water and chilled drain and KOS during replacements. While selection, we are facing some of the issues because HPCL Vishak refinery is under expansion project. We have the limitation in our plot area. So our major problem is the plot requirement, and second one is the electrolyzer life and cost of the electrolyzer. Nowadays, so many vendors are available for electrolyzers, but the key criteria we followed is the life of the electrolyzer as well as the cost of the electrolyzer. Further, we are considering first because we are giving the EPCC to Technip. Technip is the contractor which will provide the support to HPCL. but is not an expert in the manufacturing of electrolyzers. So he took the support from other manufacturer of electrolyzers. So in that way, we are going for DJU, deed of joint understanding between the OEM of the electrolyzer as well as the EPCC contractor. So instead of that, there are so many electrolyzer manufacturers are available. So to finalizing the tender, we are releasing the tender, and we are considering the NPV value, that is net profit value, which is estimated the cost of electrolyzer and the life of the electrolyzer, and what are the consumables required for this project, this process for the one life of the electrolyzer. We are evaluated total cost, and based on the cost, we are awarded the tender to Technic. This is the pictorial setup of our project. The stacks are showing the anode and cathode stacks, and bottom is the electrolyzer setup is there. And next to the that picture is the purification system. There is the stack container and purification containers. So the implementation challenges are, it is the new technology in a refinery. So there is no proper guidelines are available to venting of exhaust streams and everything. So that is the reason some statutory regularities are difficulty in identifying. This is the plant area where the plant is set up. The right side top section is the stacks, and bottom side is the PLC container. There is the present status. There is a substation is constructed, and electrolyzer containers and PLC containers, those are placed in their locations, and the cable working is in progress. Most of the jobs are complete, except cabling works, minor works are pending. So in a summary, it is a new challenge for us to set up a green hydrogen plant. As earlier presentation, Steve told that we can use treated water. Instead of fresh water, you can treated water is also used. So we are also exploring the possibility after set up this hydrogen unit, we will shift to treated water, which is economical based on condition. Thank you, sir.
Thank you, Mr. Raju.
With this, I thank all of you for being present in this session. Enjoy your day. Thank you.
Thank you. Thank you.